Hello, everyone. It's a little bit loud. Yeah, thanks. It's really great to be here, and yeah, thanks everyone for allowing me to come in and talk a little about using deep learning for user authentication. So the problem that we work on, it's called implicit authentication. And it's basically the ability to authenticate a human, like the person, based on their unique behaviors without them having to make any kind of explicit action. And if you think about this problem, this is not a new problem. This problem actually predates technology. And how do you identify people? I mean, how do people even know that it's me? It's because I have a name tag. Maybe some of you, maybe you've seen me before. I know, when I talk with somebody, they identify me as John, and then all of a sudden, that's how you're going to be able to identify me, or from my face, or my voice, or the way I move around, or my clothes, or all of these things, right? And this is the way that traditionally people have done authentication, and it's only very recently that with the advent of technology, that people have actually been using things like passwords or multi-factor authenticate, two-factor authentication, something a token you carry around, or again, a physical key, or like these type of things. It comes down to a fundamental question about, well, okay, how do you identify people, and what is it that makes you who you are, right? And a large part of what makes you who you are is your behaviors. And people are very much creatures of habit, and it turns out they're very, very unique, and they're also very predictable. And so the combination of those actually makes it possible to authenticate people based on just their unique factors, right? So we strongly believe that you're not the 9-digit number, and you're not a piece of plastic with your photo on it, and you're certainly not a password with a capital letter, a number, and a symbol. So yeah, this is me. You know that it's me because it has my name under the picture. I'm the CEO of a company called UnifyID. I was previously at another security company as well. I got my Ph.D. at Stanford, and in the compilers and security space. And then since then, I've been doing a lot more work on machine learning. So basically, what we do is, we have this authentication platform that can authenticate users with a high level of accuracy without requiring any conscious user action. And so we think this is going to be an important form of technology going forward. And there's a lot of challenges in going from like the idea of we're going to authenticate you based on these factors to actually making it work in real life, because it's not that hard to be able to come up with something that will work in a limited test case, or something with a small number of users, or where you have very sanitary data. And so the majority of the challenges come around from how do you actually make something like this work in real life. And so we've been pretty successful so far. So let me talk about some of the factors that we're currently using and we find that are really useful. Gait, so basically the way that you walk, and there's the accelerometer and gyroscope in your phone is incredibly precise. They are so the sensors are so precise that you can actually fingerprint the sensor. So there's individual manufacturing defects in a sensor that make it unique among all of the billions and billions of accelerometers that have been manufactured. And it's even possible to just sample these. To sample if you're able to sample the accelerometer, then you're able to actually fingerprint it, and you can tell which of any of the billions of phones, for example, that you're connecting from, and this regardless of using Tor or any other type of technology. And in fact, it doesn't require any permissions to access the accelerometer. You can go to a mobile website, and then they can then fingerprint your device. And the reason I mention that is it just points to how incredibly precise the sensors are. And also the fact that they're now pretty ubiquitous. I mean, basically at this point, every smartphone has an accelerometer. Like the vast majority of them have gyroscope and many other sensors as well. And so, this is me. This is my co-founder. We're the same height, same build, even have the same shoe size, and we seemingly walk the same. And but if you look at the center data, it tells a little bit of a different story. This is graphing the change in accelerometer. Like we went through on the X and Y axes, and then as you can see, there's a slight, you can visually see there's something a little bit different, even though we seemingly walk the same, right? And ultimately, we're able to get like a very high level of accuracy, just at 98%, with in terms of the true rejection rate. So that means that it's, when we have an attacker and it's not me, then it's correctly identified as not me. And so like we're able to get a pretty high rate there. I wanted to share this one as well. Like, this in terms of the accuracy level you get, like whenever in a machine learning crowd, you want to talk about like show confusion matrices, and if you see some confusion matrix that looks like this, like on a 264 class problem, then like, that like there's some that you have a good that you have a good solution. So we're able to get and this is on a 264 class problem. So if you think about the problem that we're actually solving, it's actually easier than this because it's not an identification problem, it's a authentication problem. So identification is, here is some data, who is it? And then authentication is, well, here is some data, is it me or not? And that the latter problem is much easier than the former problem. Right, and then so we use a lot of other factors as well. We use things like how you hold your phone, and and how you sit down and stand up, and the places you go, and other signals from devices around you. And that's really the key to like getting high levels of accuracy, is because you're not like, even with something like gait, you're not always walking. The gait works best with the phone is in your pocket, but like sometimes people don't keep their phone in their pocket, right? Or they keep it in their hand, and so maybe it's that becomes less accurate. Or you're sitting at your desk, and so you can't use those factors, right? I mean, likewise, and you can go down the list of like any type of technology, or factor that you're going to be using. It's going to fall down at some. There's going to be too many gaps, and so that's why you have to use like a large number of factors together, and then that ends up presenting a lot of challenges. But ultimately, we're able to get a very high level of accuracy. Just with 100% passive factors, just like using from the things on the phone. And I mean, the real reason why this is possible, why can we do this now where we couldn't do it before? I mean, number one is like the sensors, like the fact there's sensors everywhere. Like it used to be that wasn't the case, but now we have high quality sensors and they're all interconnected, and so this is possible. The security problems hit the breaking point. So now if you like with passwords, and identity theft and all of these things, if I think if 10 years ago, if you would have told somebody, okay, we're gonna track all of these things about you, and it's gonna help your security, like people would say that's creepy and like I don't want to use it. And now, it's like the problem is has become such a problem. The authentication and security problem and authentication problem has become such an issue that people are willing to, for example, share data, to be able, or give access to this type of data to be able to, because they're getting some value from it. And then the last area is, importantly, is like innovations on the machine learning side, both in terms of the fact we can do end-to-end training, the fact we can now take very large sets of data and not have to handcraft features and things like that. Like that really makes this kind of thing possible, whereas before it wasn't. And so GPUs play a big part in this as well. So that's really why that can be done now. And so basically the way the system works is you have data comes in from all the sensors, and then we do a lot of processing locally on the local device. So feature extraction and sensor fusion and other processing on the local device. And then ultimately, we extract some feature vectors, and then most of the machine learning lives in the on a cloud service. That it tried to figure out what is it that makes you unique, and what is different about you than anybody else. And for different people, that's going to be different things. Some people would be like they have something particular about their gait, or like the way that they hold their phone, or like whether they put it in their pocket face down or face up. Like these are all things that are like just parts of the habit. And any of those individually, it doesn't give you much information, but you combine a large number of these things together, and then each of them will give you like a few bits of entropy, and then you can eventually get enough bits that you can use this for some kinds of authentication. So let me talk about some of the real world challenges in actually implementing this kind of system, right? Because it all sounds great, and it's clear that it's clear to us at least, like in the future, your authentication is going to become much more continuous and much more seamless. So like you're going to walk into your house, and your house will recognize you. Your car will recognize you. Even businesses you walk into are going to recognize you, and they'll give you a very personalized experience. And you're not going to have to really do anything. And most of the interactions are going to become, rather than having these points of friction where you say, I have to authenticate who I am, I have to type in a password or a PIN, or these type of things. Things are going to become much more continuous and much more seamless. But there's a lot of challenges in actually implementing something like this in the real world. So I split it up into 4 categories: enrollment, performance, accuracy, and security. So on the enrollment side, this is basically, you think, well, how do I actually learn what your behavior is? And I need to be able to kind of watch you do things. Now there's 2 ways to do it. You could do explicit training, where it says, okay, hey, I'm going to walk now, and then you watch you walk, and then we extract that out, and then we say, okay, and then we figure out what those features are. Or I'm going to be, holding my phone, like I'll take out my phone 10 times in a row, and then do things like that. So that's from the point of view of a user, like they don't want to do these things, right? I mean, and a lot of the value goes away, because the value in this type of implicit authentication solution is not necessarily on the security side. It's also about the user experience and improving the user experience. So like forcing the user to do things to enroll just is not it's not really feasible in the real world. So we basically have to do implicit training. So that's basically what it means, is that we just watch you do things, and then over time, like we'll see enough instances of you doing these actions that we can actually start to build some type of classifier, with at least some level of accuracy based on that. And so, I mean, the first challenge you have is, before you can do anything else, is like detecting when somebody is actually doing some action. Because if you think about like the pipeline of sensor data comes in, and then on the other end it's like like you versus not you comes out on the other side. There's a lot of different stages of the pipeline. The very first stage is figuring out if you want to look at gait, for example, am I walking? And it turns out that this is like not this is a non-trivial problem, because for some of the things you have like a step counter on your phone that like will kind of help out and say, oh, it looks like you're walking, or things like that. But then for some other behaviors, like we just be able to like having a whole bunch of noisy real world data. If you're not careful, you end up having a lot of false positives. So things when I'm not doing an action but it's triggered as that action, or false negatives as well, like where I just miss, where somebody is actually doing something and I miss it out on it, right? And so building a detector that can reliably do that in a really low cost way is one of the big one of the hard technical challenges, right? And then in terms of training time, like how do you minimize training time? If you think about like I want to match on all of your behavior, and if you just use the example of gait, like how you walk, right? So many people, they have different kinds of shoes. Sometimes they are, sometimes they're tired. Sometimes they're walking fast or walking slow. Like so, and if you want it to be robust, then it's like, well, you really need to have, be able to deal with all these different cases, right? But you can't really say. But if you then require, say, well, you're not going to be trained until we've actually seen you do all of these actions, then that would really extend the training time for a long period. Because you'd have to look across somebody's behavior for months or years to be able to kind of get high levels of accuracy, right? And so there's some techniques you can do on that side is the fact that once you have a large enough set of data and you've seen enough people do for example, walking slow and walking fast, and then you can then build a generative model that can say, well, I've never seen you walk quickly. I've only seen you walk slowly, but like I know how people in general, how this transfer, typically works for people, and then so we can then use that to augment the data, and so this becomes this type of data augmentation becomes a very important technique to be able to make one of these systems work in the real world. I mean, partially because we want the system to be able to work well in many different scenarios, even ones that where it hasn't seen specifically for you before, and we also want to leverage like the intelligence of the crowd and the fact that there's a million other people on this, and then be able to leverage some of that knowledge about human behavior, other people's behavior, to actually influence your own. So performance. So in order to get this to work well, it has to be low latency. Like we have SLAs on our product where within 10 seconds of you putting a phone down or somebody else picking it up, we need to be able to detect to say, oh, this is no longer you, right? And so that there are a lot of challenges in that to making that system actually work, and I mean part of it is in terms of just making the machine learning algorithms efficient and work online, but that's only one part. I mean there's latency and actually the detection time and the response time. And then, scalability concerns, as you're growing this, as you get to more and more users, you can't, the system has to be able to scale well, right? And then, so you leverage a lot of on-device machine learning, machine learning in very resource constrained environments, right? And so that brings in a lot of techniques that we use, instead of using full precision neural networks, you can use reduced precision, all the way down to binary. You can go all the way down to binary neural networks where all the the activation weights are one of two values, and so there's these are the type of things that you end up having to do if you are to make things work well, actually running on a local device. So there's a lot of technical challenges on that side. On the accuracy side, so the biggest thing is having to deal with the real world. So building a classifier for something where it's been caught, some type of data where it's been collected in sanitary conditions is that's in many cases that is not that difficult, but making dealing with the real world, in terms of all the different scenarios and everything, that becomes a big challenge. And I think a lot in the ML world, a lot of the focus is on just the classification piece, where it's okay, well, I have clean data coming in, and what is the output of this classifier? But that's in our pipeline, that is just one small part. And if you don't have great detection logic, or if any other piece of the pipeline is not working well, then the whole system doesn't work well. It doesn't matter how great of a classifier that you have, right? And so that's so be able to deal with that, balancing this false positive and false negative. So I really it may be acceptable to say that well, if my phone doesn't recognize it as me, then I can always go back and use a password, or I can use some biometric, or I can use some other type of, fallback, right? But I really don't want somebody to be able to like get my phone and then be accepted as me when they're not me, right? And so you have this like trade-off, and it's not like you don't want to have an equal error rate. Like you want to have something, you want to skew it in one direction, and then like how exactly you skew that is going to depend on your use case. Like in some cases, it's a high security thing, and you really need to like emphasize like being secure. Other things, well, maybe it's just for like a personalization or convenience. So like the cost of a misclassification is not as high. But this is stuff that we have to balance and try to find the optimal points for combining multiple factors together. This is also a very non-trivial problem. So we have large numbers of classifiers that's looking at all these different factors. Many of them are noisy, and then they're spitting out some information. Like how do we actually combine that together into something that's meaningful? So because like I mentioned, like in many cases, like there's data that's missing, or the classifiers are not high accuracy enough, or and have problems. And then tracking things like dependencies between these factors. These are there's a lot of challenging problems in that space. And how to do that in a reasonable way. And finally, tracking your behavior changes over time. You may have something, but I move to a new city, or I buy a new pair of shoes, or I injure my leg, or like any of these things happen, and these things cannot be static because your behavior actually does shift over time, over a period of time. But and so how to actually do that in a machine learning system? That's another big challenge. So like we basically have to have online learners that are learning all the time. Like you can't just learn a model and then say, well, this is the model for you, because that model will change over time because your behavior changes over time. And so like you need to be able to deal with that. And then finally on the security side, like we're talking about adversarial attacks. Well, I mean, in any system like this is you have real adversaries who are trying to attack the system. And so this is not a theoretical exercise. These are like what people will actually do. And then and so there's taking into account all of the different types of adversarial attacks, not only on the machine learning component, but other components as well. And then finally, data privacy and security. Like when you have, how can you do machine learning on a system, on a set of data, while still respecting the privacy of individual users? Like we can't become a honeypot for all of these like users' biometric data, right? So how can you do machine learning in these cases where you don't where you don't want to have to aggregate all the data together, or at least if you do have data, you have to think about how to anonymize it, or use use other types of techniques to be able to do that. So this is a really big challenge that we have to deal with, right? And so I'm going to talk about just four like major techniques on the machine learning side, which have had the biggest impact on our on like building a successful working system. So first one I'm talking about is data set augmentation. I think this is a extremely important technique to be able to avoid overfitting your data, overfitting your machine learning your classifier to your data, and make it work in many more real world scenarios, right? And there's the type of data augmentation that we do it really depends on the type of data that we get in. Much of what we deal with is time series data. So it's there's a timestamp, and then there's some event that happens, or sensor readings over time and things like that. And so be able to augment data with by warping the time in different ways, or things like I mentioned, like style transfer and things like that are that could make a big difference. And if you can build a generative model of and then use that to generate to greatly augment your data, and you essentially get like a free lunch, because you have a you can you have a limited set of source data, but by using some of these data augmentation techniques, you can make it you can increase the strength of your classifier effectively for free. And so there's a lot of free lunch tricks that you can do that help with the accuracy of the system. And then there's some of the relevant papers there. Second one is like you don't just build one model. Try to use a multiplicity of good models, an ensemble of models, combining combining many different aspects, even if things are looking at the same fundamental underlying process. Having a large ensemble of classifiers ultimately gives you a much more robust system in the real world. And so, because if you're looking at a very limited data set, you may feel like, well, I'm going to have all these classifiers, and I can just choose this one that's, this one seems to work the best, and so I'm going to choose this one. Like in the real world, it's much better to have more classifiers using, with slightly different techniques or using different, with looking at different aspects of the same problem in order to get stuff to work reliably. Third point is visualize. So it's so important to actually understand how everything works at every stage. I mean, visualize the data as it comes in, so you can understand what the nature of that data is. Visualize how things are working in your neural network. Which features are you actually matching on? Are you matching on things that are going to be robust features or not, right? And then if you look at things like the accuracy, if you just say, well, I'm going to run this and I get some accuracy out, that's going to depend on so many things. And so actually looking at things like a confusion matrix and understanding, oh, why are these things getting confused? That will ultimately point back to ways to improve the system. And so a lot of the time that we spend is just in basically understanding and visualizing data, as it goes through the whole pipeline. And the fourth one I want to talk about is regularize. So that means doing regularization on the inputs. I mean, that's things like using techniques like data augmentation. Throw in adversarial examples, into your inputs. Augment with those, do things like style transfer. I mean, resampling. I mean, we have time series data. We don't want what we're doing to be reliant on the exact sampling rate or patterns of what of a particular signal or the exact timestamps of when things happen. And so the good way to avoid that is to basically to these, and these are cheap to do. I mean, it's so cheap to be able to generate a bunch of resampled versions of data, but it really helps to regularize and make sure that you're not overfitting your system. Within the network, use all the standard techniques. I mean, use dropout, Gaussian noise, weight penalties, early stopping, all these things, because you want to make sure that you're not overfitting to the system. Because again, it's even if you get something. You get something that seems like it works and gets a high level of accuracy, and then when you test it out on more data or more real world data, then you realize that you're massively overfit. And then regularization on the labels. So things like label smoothing. So instead of just saying, well, this is this walk cycle is 100% me, or 100% the person X. You take and you spread it out, across multiple many different labels, and so it's no longer like a binary, like a sharp binary yes or no, but it's much it's smoothed out, and then using this technique you can get you can make sure that you're not overfitting on any particular aspect, and or things like softmax labels from teachers, and there's a number of other techniques as well. But in terms of actually getting things to work in real life, this is one of the most important important aspects of understanding how to do regularization with across every layer, like from the inputs to your network to the labels as well. I'd almost out of time. Just wanted to mention we have a great team, a great work. We're also very active in the research community. We have an AI fellowship. If any of you guys might be interested, we basically support you to do interesting research work, and we've had a great cohort, basically twice a year. And then we're pretty active in the research community at ICML and NIPS and security conference and stuff like that as well. So and you can find out more on our website. But anyway, so that's all I have. I'd like to open it up for questions if anybody has any questions on any area. Yeah.
Is this on?
Yeah.
It is? Okay. Thank you for that talk, John.
Yeah.
My name is Terrence Sim.
Mm-hmm.
I'm a faculty member here. I've been working on continuous authentication for some time, so I understand what you're doing.
Mm-hmm.
So a couple of questions. One, do you have an actual product now? Or because you haven't actually said anything about a real product.
Yeah. So we have a product. So I'll talk a little bit of the product side. Most of our customers, we have many customers like financial services and banks and like social networks and a few others that are deploying our system, but not so much for completely replacing all of their authentication, but it's for more things like I want to get a risk score of how likely it's you, or I want to streamline the authentication in some ways.
So you're saying you do have something running on the smartphone?
Yeah. So it's on that side it's for iOS and Android, and then we have we have iOS and Android versions, and then the way that we ship it is we have an SDK you can link into an existing application that gives us access to the sensor data, and then we provide an API that you get you can query the score.
Okay. And the other question, very quickly, is what are the biometrics, or what are the sensors that you use?
Yeah.
Number one, and number two, how do you avoid draining the battery?
Yeah, very. That's a very important aspect. So the sensors that we use. So we use. We can get away with just having accelerometer because you can get a lot of information just from the accelerometer. That's the minimum. But we'll use gyroscope, magnetometer, GPS, Bluetooth, Wi-Fi, cell tower, barometer even, and those are the examples of the type of stuff we do. And some things with interactions with the phone when you unlock the phone, these type of things. And so if you think about there's almost a dozen sensors on a modern smartphone, and they all provide valuable information. Now you can't just leave it recording all the time because you will very quickly drain the battery. And so this is why it's important, like I mentioned about how on the detection aspect, how to actually detect when somebody is doing something. You can't just you need to have very low cost detectors, so there's trigger events and other things that happen that based on when a trigger happens or what time has elapsed. So we will pull periodically. We won't actually be recording all the time or monitoring all the time. And then there's a trade-off there in terms of the actual detection versus the battery drain. But the goal in the product is to make sure that that we don't have a noticeable impact on battery, because then that will really make it so people wouldn't want to use the product. So.